So I'd like to thank the organizers for inviting me. It's a delight to be here in this auditorium celebrating Deepak. And I love this blackboard. And I remember a few years ago starting there and filling it up to there. And it's just a delight. So what I want to tell you today, as Sriram said yesterday, when he already spoke, was now for something completely different. Okay, so this is going to be much more of a soft matter talk, and so hope you like it, as they say. Okay, so the question is, can we define random close packing? And this is work done with Paul Chaikin at NYU, his former student, now a postdoc at Santa Barbara, Sam Wilkin, his former postdoc, now at Impossible Meat, I believe it is, Rodrigo Guerra, which is, I'll tell you later, Shuna. And current postdoc of ours, Ashley Guo. And so, yeah, there we go. So the general question is, what's the densest packing of identical spheres? And so there we go. So in MDCXI, Kepler wrote this book, and in it, he conjectured that the densest possible packing of spheres was in this arrangement that we see over here. Now, that was 16 something or other, I forget when, 1611, thank you, Sriram. 1611, and well, before I tell you more about these guys, the arrangements that Kepler was proposing have a volume fraction of 0.74, just that number over there. There are various periodic arrangements, FCC, HCP, there are other stacked arrangements, doesn't really matter. Those are the two best known. Cannonballs, this is a useful talk, okay? So that was 1611. My guess wasn't that Kepler was the first, but he was the first to write a book on it. But I don't know. I say, okay, you give me the reference, Paul, and I'll put it in. In any case, however that might be, it took another 200 some odd years for Gauss to prove that indeed was the densest lattice packing, crystal packing of identical spheres. So Gauss proved it in 1831. The two-dimensional problem is much easier, okay? This is actually quite difficult. And it took another 170 years roughly for Thomas Hales to prove that this was in fact the densest packing of identical spheres of any type, whether it be lattice or disordered, if you like, okay? And that was quite a tour de force. The Fields Medal this past year was given to a mathematician who proved the same thing in 8 and 24 dimensions. These are special dimensions. And so this was, she won the Fields Medal for that. It's again, these are tour de force pieces of work. Good. But this isn't what you get if you pour ball bearings into a giant container. Then you get something like this. Well, these aren't ball bearings, they're marbles. And it used to be that you'd go to various carnivals when one used to go to carnivals, when there used to be carnivals, and they would have some big thing set up like this, and you had to guess the number of marbles in there, and if you guessed it, you won a cat or something. You won something. Okay, I mean, guessing it, get the closest one to it, and so, and this arrangement, and how do you get it? Well, what they get is pour these things in under gravity. There are other experimental methods, typically involving pouring hard spheres into some container, shaking them, jostling them, treating them badly, and then they densify until they get to this random close packing state. And it is typically the case, almost always the case, experimentally pretty much always the case, that the density, the backing fraction of such an arrangement is around 0.64. Okay, so the question is you can ask why 0.64 if you like, and that's a perfectly legitimate question. Bernal studied this in 1960. Scott studied it in 1960 at the same time. Sid Nagel revisited the problem in the late 80s, early 90s, probably early 90s, and they got the same density. So this seems to, so the lore is that basically no matter what you do, you pour a bunch of hard spheres into some container, and provided the container is large enough, this is the volume fraction you're going to get to. Okay. So the question is, I mean, so how can we define something like that? It's easy to define a crystal packing. Anything with order, you say, well, I'm looking for an arrangement with this order, right? Some sort of broken symmetry. I identify it through a broken symmetry, so I sort of understand how to do that. If I don't have any such thing, then I don't know how to define it. So fundamentally, how do you define something, some configuration, which is sort of defined through the absence of equality? And that's the question I wanna place in front of you and try to give you some sort of an answer. Anyway, there have been a couple of attempts to discuss this. Torquato and his collaborators proposed that you can define what is equivalent. They give a different name, but the equivalent of random close packing of hard spheres. By looking at a set of order parameters and looking at the packing which minimize them. The problem with that is there are always other order parameters which you haven't thought of, right? And so this can't serve as a definition. Other people, O'Hearn et al. And other people have proceeded with that as well, have said, well, what's actually happening, the reason you always seem to see this is because the basin of attraction of the set of when you started some configuration and you do whatever dynamics it is which is going to lead you to the packing, the basin of attraction of 0.64 density arrangements is the largest. That's what they would say. But that sort of depends on how you do the simulation and what the protocol is, as Shrikant knows better than anybody else. So you have to, so this wouldn't serve as a definition either, although it is certainly very nice. Okay. But I want to make contact with what people seem to think is random close packing. So I have to tell you a little bit about how people get them. So the most common algorithm is the Lubachevsky-Sillinger algorithm. And what they do is as follows. They start with a bunch of point particles, let's say, I don't have to do it this way, but it's easiest to state this way. Start with a bunch of point particles which have some sort of energy to them. So they're moving around, okay? And what you do is you swell the particles at some rate, and eventually they will jam and they won't be able to move anymore. So the parameter, given that you have a certain energy defined, is the swelling rate. And the thing is, if you look at as a function of swell rate, the ultimate density that you find is dependent on swell rate. If you swell it too fast, then you get a lower volume fraction. If you swell it too slowly, you get a higher volume fraction. And so what you do is you stop the simulation when you get to where you want. And I mean, you say, well, I'm going to look, I know where I want to get to, and I'll fine tune the swell rate. So that is, again, not very much of a definition. You have to avoid certain things by hand, like crystal regions. Okay, so what's known about RCP? Very quickly, RCP configurations are isostatic. That means they're minimally stable. Now, the way you would, I suppose you could say there's the same number of constraints as degrees of freedom. Each sphere has 3 degrees of freedom in 3 dimensions. And therefore, there are 3n. If you have n spheres, 3n degrees of freedom. I'm not worried about the minus, about subtracting out the overall translations. The rotation doesn't bother me much. So if the jth sphere has z sub j contact points that are constraining its motion, the total number of contact points is just n by 2 times the average of j, because each contact point is shared with 2, factor of a half. So there, if I want these two to be equal, then what I find is that the average number of contacts should be 6. That's called an isostatic packing. In more generality, in d dimensions, you just get twice the dimension. It's different if you have friction. Okay, if you have friction, it's a different story, but there's no friction here right now. Okay. Other thing you can look at is the pair correlation function. People often look at that as a means of understanding the structure, and what this pair correlation function is, just for those students who are new, it's the probability of finding a pair of particles some distance separated by some distance, and so you can't, of course, have, if these are hard particles, you have a hard cutoff on the left. There are a couple of, I don't know if I have a laser pointer here. Do I have a laser pointer? Yeah. There's a characteristic feature, this split second peak, which looked like Batman or something like that. And the other thing is you have a characteristic drop off from touching. Now that goes by the name of, so if this measures the gaps, okay, between the spheres. And so I'm going to come back to this. This decays with a power law, and according to this group a long time ago, the gap exponent, what's called now the gap exponent, is minus a half. Okay? Yeah.
Is there a delta function at 1?
Is it a delta function at 1?
In G of R, is there a delta function at 1?
Is there a delta function at 1?
Because you said there have to
I think there has to be, right? Well, does it have to be? Yeah.
Okay. And then there is still some region in which it is not 0 immediately after.
I mean, to the extent that, to the extent that people do simulations and of finite size, I think that's the case, no? Yeah. No, it's diverging the other way. Yeah.
That
diverging the other way.
Strange to me just now.
That
sounds very strange to me, but we can discuss later.
Okay. In any case, this is so I'll come back to that point a little bit later. So we saw some years ago that this fell off with a characteristic power of half. Okay, and we'll come back to that a little bit later. Okay, so basically, we'd say, I mean, on the minimal aspect that the minimal things that you demand from something which claims to be random close packing is that it be isostatic and that it have a G of R which looks like that with whatever characteristics you can derive from those points. Okay, so let me now switch gears and tell you about a model called random organization. I'll do it rather quickly. It's an absorbing state dynamical model, so this is why perhaps it's appropriate to this meeting. So in random organization, the simplest possible model is, this was a model Paul Chaikin came up with to understand some data on sheared non-Brownian particles, Dave Pine and Jerry Golub. In any case, you have the system is like this. You put particles down at random. They have a finite size. If they are alone, you don't do anything with them. And if they overlap, you give them a random kick. You just randomly move them. Okay, some amount, some distribution. Take a flat distribution between 0 and some maximum, whatever it might be. Okay, that maximum kick size is in fact a parameter in the model, and it will change certain things but it won't change the more interesting things. And you're going to continue this until there aren't any active particles or until the activity level's off. And as Sriram and Gautam Menon showed a while ago, this is an absorbing state model in the mana universality class. Okay. And here, this is just because to show you that I know how to do minimal programming in Keynote. For this particular example, if there are more than 2 particles in the box, let's empty the box and redistribute the contents randomly to neighboring sites. So I'll do that, and I'll do it again. And I mercifully didn't do too much. And now everybody is happy because everybody has fewer than 3 balls in the box. So this is now an absorbing state. Dynamics is over. Had I put more in, the dynamics would continue. Had I put sufficiently high density. Okay. So a sufficiently high density is in fact something above what I'll call rho C, which suggests to you that which you already know, that this is a critical density. The fraction of sites or a fraction of balls which are active is the order parameter in these transitions, and you have the active fraction as a function of density is 0 in the absorbing phase, of course, and then it rises with some characteristic exponent close to rho C, and this is all well studied for a variety of models. Okay, the interesting thing, as far as I'm concerned, is the fluctuations in particle numbers, something I talked about a couple of years ago here. Probably here, and certainly at the TIFR. For a random distribution of points, the variance of the number of particles in a window of size L, so I'll take it to be circular here, it doesn't really matter, scales as L to the power D if I'm in D dimensions. On the other hand, if I have a crystal lattice, and to make life easier, I'll just slightly shift all the points just to avoid having any issues. The variance scales as L to the D minus 1. Okay, so you would say, well, generically, the variance might scale as L to the D minus alpha. And then if alpha is less than 1, your distribution is less than perfectly random. Okay? And what we found was with Daniel Hexner a few years ago, was that the critical states of this class of models had that property. The variance in the number fluctuations was less than random, more than periodic, but less than random. That is to say, alpha was positive. So this has reduced fluctuations at criticality, and this is called hyperuniformity, typically. And the values of alpha are characteristic of the mana class. So you can use different models and you'll get the same values of alpha. It's, of course, dimension dependent. Okay. Here's a picture of a critical state from the random organization model in 2 dimensions. And here's just some random non-overlapping or not particularly overlapping set of, at the same density set of disks. Okay, that's fine. You can also see this in the structure factor, which is effectively the square of the Fourier transform of the 2-point function. And the only point I want to make is that you see hyperuniformity through the structure factor if the structure factor at small k, that is to say large scales, large real space scales, small k goes to 0. Now, for me, I'm only going to think about cases where it goes to 0 as k to the power, some power. And as it happens, that power alpha is the same alpha that we found a second ago. Okay? In other words, these two things are connected. So the structure factor and the number of fluctuations are connected. They have the same exponent, although they come in different ways, of course. Okay. Good. Now, let me change the model just a little bit, and we'll bias things a touch. Before, when we had overlapping particles, we moved them at random. Okay. Now I want to bias them to move apart a little bit. So they move apart a bit. They also have some, in principle, they have some amount of random motion as well. Okay. Excuse me. The maximum displacement is epsilon. Delta tells you how much randomness I have. So and it goes between 0 and 1. So this is now what it looks like. If delta equals 0, we get back to the previous model. Okay, delta equals 1 just separates them with no randomness, and the critical behavior. I'm not going to show this to you. The critical did quite a bit of work to show this. The critical behavior is the same as the mana, as the regular random organization model was, which is the mana class. Okay, and in particular, that exponent alpha, which characterizes fluctuations and decay of the structure factor, is about a quarter. Okay, just to make that, talk about that later. Okay, so what do we find for critical states in this model? Well, in this model, it depends on how much randomness you have and how large the maximum kick is. That's also true, by the way, for the random organization model. If I move particles further, I'll eventually come to a critical density, and the critical exponents are the same irrespective of the value of epsilon, the kick size that I choose, but the densities are different. So it's sort of like, if you like, you change things up on the Ising model, the critical temperature may change, but the exponents don't. It's the same sort of thing going on here. The point is that as the maximum kick size, epsilon, goes to 0, these guys seem to converge to the same critical density. So we've only shown it for you can see it for the blue and the red curves. The others will join it as well, except for the bottom one, which is just random organization. It's flattened out. It's going to stay there. Okay. So it doesn't matter how much randomness you have. In the limit, as the kick size goes to 0, you tend towards critical states whose density is about 0.64. Okay. Then we looked at the structural characteristics. So this is what the pair correlation function looks like. Has very similar. It looks very similar to what I showed you before, and in fact, it does. I mean, when we overlaid it, I didn't do it here, is a limit to how much one can show. It overlays nicely on what's generally accepted as random close packing. So from other methods, so things are okay. Has that Batman second peak in the limit of small epsilon, and in addition, so have I run out of batteries, or is it? Come on. Yes. That was that. Good. It has that 1/2 slope, or that exponent of which scales, the gap exponent scales the way I showed you earlier as square root. Okay, so we were happy about that. So we then of course you what's the thing you declare victory and retreat? Is that that's the usual way of doing things? So we declared victory, but then we didn't quite retreat just yet. So let's look at the structure factors. So this is S of Q or S of K. I've overlaid 3 different ways of arriving at these random close packed states. They overlay quite nicely. It's a logarithmic plot. It's a log-log plot, which is important to do. And this comes in with an exponent. So S of k goes to 0 as k to the 0.25, which is the same as the Mana exponent that I claimed before. The exponent, the hyperuniformity exponent for the Mana class that I claimed before, I should say. There we go. So what about other dimensions? I might actually finish, in time. This is going to be, there should be a prize for that. Good. What about higher dimensions? If we want to make the claim, which we do, that, so before I talk about higher dimensions, the declaring victory is now to say the following thing. It's to say that we propose that random close-packed structures are the critical configurations of a well-defined dynamical model in a well-defined limit. Epsilon goes to 0, biased random organization, starting from a random initial conditions, because people know if you start from a carefully chosen initial condition, you can get different things. So this is the measure 1 answer. And so if we're right, this would provide a definition of random close packing, which of course circumvents the necessity of discussing what's random and what's not random, which is a fool's errand. There's no way we could do that. Why would you care? Well, aside from the intrinsic amusement that we get from it, it suggests, if this holds in higher dimensions, that you could, in principle, try to get results from higher dimensional systems. Okay? And then maybe one could actually do something analytical with this problem. Okay? Which seems otherwise pretty hopeless. Okay, so what about our other dimensions? Well, so as a function of epsilon, so let me just point out there's a bunch of things going on here. D equals 3, I've already showed you. Now what we're doing here, this is a critical volume fraction as a function of maximum kick size. So that changes, as I told you. If you kick things more violently, you'll eventually come to there will be a critical state, okay, separating active and absorbing, but it will be less dense than something which is kicked more gently. Okay? And we're looking again in the small kick limit, and the epsilon goes to 0 limit. So D equals 3, I already told you a bit about. So that's over here. So as epsilon gets smaller, the critical, so each of these is a critical volume fraction of a critical state at these different maximum kick size. Okay? And it's quite nice if you plot it logarithmically, things flatten off. But here you can see that things really tend linearly to a well-defined volume fraction, as I told you, was 0.64 in 3 dimensions. In 1 dimension, shockingly enough, it tends to 1, because sort of what else could it do? Okay. 2 dimensions, it tends to 0.91. 0.91 is maximum packing of identical disks. And the reason I even bring this up is because there's a lot of discussion recently on whether or not you have random close packing in 2 dimensions, random close packing of identical disks in 2 dimensions. And people have religious fervor about it. And so in the interest of religious wars, we want to come out and say that these don't exist, that there is no random close packing of disks, and then get attacked. But that's okay. So that's the point about D equals 2. What about D equals 4 and 5? So D equals 4 and 5, again, behavior looks similar, and you cross over and you get a critical density of around 0.46 for 4 dimensions and 0.3 for 5 dimensions, which are consistent with other algorithms done by other people. I'm really fine. I'm speaking slowly because I just don't want to. Hang on. Oh, you can ask a question. You can screw me up.
Yeah.
Speak up, seriously.
Did you
Right.
try polydispersed disks in 2D?
2D, yes.
Polydispersed.
Pardon?
Polydispersed disks.
Yes, we did.
Okay. You're going to.
I mean, they obey the same sort of things that they should. They fall into mana class. They have the right gap exponent, all this stuff. But I don't want to get it. It's a bit too technical. Yeah, but we did. Is not? Sure it is. The limit exponent for bidispersed or polydispersed. Sure it is. Sure it is. Yeah. They won't, but we won't get to those packings. No, we won't get to those packings. No, we won't get to those packings. No, it's not perfect in the sense that it's not crystalline, right? It's not even the densest possible packing. We get the density of what's conventionally called random closed packing. Oh no, 0.9, no, 0.91 in 2 dimensions is a crystal packing. In 2 dimensions, I'm sorry, in 2 dimensions, yes. I don't believe that if you give me a random distribution of disks in 2 dimensions that you'll always get the most. No, I don't.
That was, I guess, the question.
Might have been the question. Oh, okay. Was that your question? You might as well say yes, because, okay, very good. So yes.
One more question. Is there a proof that this linear extrapolation
No.
is exact?
No. I mean, you could have stopped at is there a proof, and the answer would have been the same. Irrespective of the continuation. Okay, so those guys are periodic, right? So those guys, the 1-dimensional, 2-dimensional packings that we get are periodic. And now I'm just talking about the gaps again. And so the gap is the closest approach to particles we'll have, okay? And it was shown by Charbonneau, Foche, Korchan, Giorgio Parisi, Urbani, and Zamponi that in a really rather tour de force calculation, full replica symmetry breaking calculation in infinite dimensions, that that exponent, that gap exponent that I previously told you was a half, was 0.41 roughly. Okay, so this is a calculation which is really quite glorious, and it gives you a number which is really quite nice. Now, several of these people claim that this is true in all dimensions, that you get the same number for all dimensions. I want to dispute that, but I'll do that in just a second. Okay, so let me just look. So here, let me dispute it right now. Okay, so I've shown 2D, 3D, 4D, and 5D, and it would work by the, sorry, 2D, yeah, 2D is a bidispersed. Shrikant, wake up. This is 2D is a 2D bidispersed. Okay. And the values of gamma, that gap exponent that we find, is in 2D 0.58, 3D a half, as I argued before. 4D and 5D is spot on to where these folks predicted for the infinite dimensional case, okay, which is quite nice. We've modded all that the behavior out. So flat means at that exponent, okay. So this is what we say, and then you say, well, what about hyperuniformity? So okay, let me. I'm gonna really blow it. Just trying to get under. No, it's because of the questions. It wasn't because of me. I would have easily made it. In any case, so the 3-dimensional, I've already shown you that the 3-dimensional random close packed structures that we get. And as I said, they match. This is also true for RCP structures that are obtained by, let's say, Lubachevsky-Stillinger. We have some people are kind enough to give us, I have 35 more minutes. I'm fine. Yeah, this is the problem with ADD, is now I don't know where I am. Thing rings and I'm gone somewhere. So I showed you that in 3 dimensions, the packings are hyperuniform. I told you what the exponent was. Okay. In 2-dimensional bidisperse, they're also hyperuniform with the expected monoclass exponent, which is some years ago, we conjectured, again, not proven, that the hyperuniformity exponent is 2 minus the correlation function exponent. Seems to fit. That's the and so this works in 2 dimensions as well for bidispersed systems. Of course, monodispersed disks is a different story. And if you look at that, so the mean field value of the correlation function exponent eta perp is 2. And in that case, you'd expect alpha equals 0 above 3 dimensions, d equals 4 and above. And sure enough, we find that you get that exponent for 4 and 5 dimensions. What does that mean? It means that those packings are not hyperuniform, which is sort of you might argue it's a very strange thing. So in 3 dimensions, you have a hyperuniform random close packed structure. 4, 5, 6 to infinity. You don't. They have random fluctuations, and so that's sort of an odd thing. So the point is that we're claiming that that 4 is the upper critical dimension of random close packing. In this sense, right? In the sense that we can, and this follows from our identification of the configurations as being those of the critical states of this model. Okay, so that's sort of an amusing thing, and that's consistent with what I showed you a second ago. 1 second, Sean. That's consistent with what I showed you a second ago about the gap exponent. Okay, being different from 0.42 in 2 and 3 dimensions, despite claims in the literature to the contrary, and being 0.42 in 4 and 5, and we'll eventually look at 6, 7, and depending on how many students we have, and how highly we regard them, 8, 9, 10. There we go. So let me conclude. So these are the declaring victory and the retreat part. So RCP, we claim, can be defined as the critical states in the small kick size limit of a well-defined absorbing state model called bias random organization, which is in the Manna universality class. Okay, that's the claim. In 3 dimensions, random close packing is hyperuniform with characteristic exponent of that class. The upper critical dimension of RCP is 4, consistent with the Manna class. And we get the correct, or correct in the sense that they agree with other people's work, densities in 4 and 5 dimensions. And in 1 and 2 dimensions, we only get periodic lattices. So we're going to now go out on a limb and say that there isn't random close packing in 2 dimensions. As I say, because we want to make our friends dislike us more than they already do. And what that would say is that 3D random close packing is the least random of the random close packings, in the sense that it's hyperuniform. All the other ones are not, or they're periodic. Thank you very much, and I'll try to answer.
I had a question. Hello. Hi. So you had a graph of the G of R versus R. and it had singularities at 1 and 2 and √3 and various numbers. Are the nature of singularities other points also known?
I don't think anybody studied them.
Okay.
So yeah, I don't think anybody's.
It looked like they were singular at other points.
They may very well be, and I mean they do have that. Yeah, I don't know of anybody who studied that, but indeed they do look cusp-like. Yeah, that's.
So
Yeah.
those cusps. Sorry. So those cusps, those Batman's cape things, they're special to 3D.
Yes, as far as I know.
Okay.
I believe that's true. I mean, it could be that people weren't able to generate packings large enough in higher dimensions. So you don't see it in 2D, in higher dimensions. But the pair correlation functions I've seen from higher dimensions don't seem to show that.
So which will be the protocol which is consistent with this definition experimentally? You just pour it, or you have to shake it, or
Yeah, you shake it. You pour it in. You shake it, right? You don't know. So what are you nodding then for? I'm shaking, not stirred. You pour it in, and then you shake it a bit, and yeah. I mean that's more or less what. So that was done by Bernal. It was done by Mason. It was done by Sid Nagel, and collaborated in Heinrich Jaeger and people
and all
working with them.
all get 0.64
They all get
plus minus
0.64,
something.
yeah. They all, yeah. The system, ultimately, they start out. It was so in Sid's case, he started them out from a denser, from a denser arrangement and a less dense arrangement, and he banged them around a little bit and probably systematically, and he found 0.64.
Then delta is provided by gravity.
Delta is provided by, well, something's provided, I don't know, delta is provided by gravity, but maybe.
Hello.
Yes.
And there also, if you vary the rate at which you inflate, that takes you to denser systems, right?
Mm-hmm.
This limiting procedure doesn't work there, or
Which doesn't?
this limiting procedure that is, if you actually look at the density as a function of the rate.
Which limiting? I mean, so in Lipschitz cylinder, you have a what's the word?
Inflate the individual spheres, right?
Yes.
And but the rate at which you do that depends on where you get stuck.
So you change that, you swell at a certain rate.
Yes. As you go slower, then you go to higher density.
As you go slower, you go to higher density. Yes.
I mean, if I look at the limit of that, then
Oh no. If you go to the limit of that and you do it right, I think you crystallize pretty well.
I see.
I mean, you may not get a perfect crystal, but it crystallizes in the sense of having crystalline regions.
Now, with the Lubachevsky's Stillinger procedure, you do get RCP, except they didn't want to say so. I think. So, I mean,
They know that?
they do get 64% with from the work of Torquato et al. Yeah, I don't think there's any problem there.
No, there's no problem. But if you swell too fast or too slow, you get something else.
Too fast, yes.
Yeah, and
Yeah,
too slow.
yeah.
It's not. You can't do it infinitely slowly and expect to get as far as I know. Sir.
Suppose I start with low density. Each of them are doing a random one, very small amplitude random. Then I increase the number of these spheres in the system. Whenever there is a vacancy, I add one, and it also starts doing random one. Then by chance there will be another vacancy, I add another one. So could that be a possible way?
I don't believe it, but it would be. But it's a cute model. I like it, but no, I don't believe you'll get. I don't. No, I don't think so. Yeah, but if you have to wait infinitely long because everything is going to open up, yeah.
So can I? The last part where you talk about the GFR exponent, that's both surprising and, as you said, it's inconsistent with what people have found in 2 and 3 dimensions. And not only the GFR exponents, but also the relationship with the exponent that Chandan talked about for the force distribution. So the gap on the force distribution exponents satisfy the marginal stability condition that has been expected, and both the exponents are calculated in the mean field theory that you mentioned. I think, and something that we have done is to also show that this is even valid for shear jamming, which is not something that was originally part of the theory. So I think that exponent being 0.4169, whatever number you put up, is fairly well established at this point.
No, I don't think so at all. I mean, it's certainly, it's
D equal to 2 and above.
no, it's certainly not, it is certainly not well established. And if you look at the data presented, it's not, we can have a discussion, but well established, it is certainly not.
So I had 2 little questions. One, where is, at the end of the game, where is isostaticity in the whole story?
Where is it? It arises as
Meaning you can measure the resulting configurations by, I mean, the configurations at this critical state are in fact isostatic.
Yes, indeed.
Numerically measured, you're saying.
Yeah.
Right. Other thing I didn't understand, I mean, why is this, you must have said it, why is the biased process necessary?
Oh, because otherwise you'll get.
I just missed.
You'll get a maximum density no matter what you do, which is much lower than random close packing. Right? You'll have you won't get things which are touching in the same way. Certainly, it'll be far beneath isostatic.
I see. But whereas, okay, if you look at the original experiments by Dave Pine, they were done by shearing stuff in some oscillatory way and things.
And they're done by jostling and banging them, stuff like that in the experiments.
Oh, that way.
Yeah. They put them in balloons and massage them. This is literally what
the dense ones. I was thinking of the sheared random organization ones. I guess those.
No. That's a different story. Yeah, there's no.
There's absolutely no contact between that and this.
Well, I mean, the same model generically, same critical exponents, of course, but no, there's no sense in which there's no shearing involved here.
No, you couldn't. Yes. No, I'm talking.
I know. We know. Yeah.
No. What I meant basically was doing those experiments at progressively higher volume fraction. In the shared way, I mean. So it seems that if we put in a protocol of shear in 3 dimensions, it crystallizes. That's all I can tell you. That's all I can tell you. So it wouldn't give you. Yes, Shrikant.
Yeah, no, the other point about these GFR singularities, something that we looked at some time ago was what happens when you athermally shear spheres, and all the GFR singularities you develop, regardless of whether the system is jamming or not, right? So it seems to be more a consequence of a certain way of bringing particles together, rather than whether it has anything to do with jamming physics. Okay, this is.
But if you have an equilibrium fluid of spheres, you don't get a.
Yeah. No, I said athermal shearing of spheres.
Okay, fine.
Yeah. So it's if I'm not mistaken, though I'm not 100% sure, the second peak simply corresponds to sort of tetrahedral and octahedral arrangements. So there's a corresponding, So I think these are just sort of, Kabir may have something to say about this.
That's true. There, you have local because.
So these are very local features.
Yeah.
On the other hand, the GFR singularity at 0 or at sigma that you're surprised about, that does seem to be a non-trivial feature. It does arise even in non-jamming contexts, like I mentioned, but that sort of has to do with progressively pushing particles out of overlap, but then you always do it in the least possible or least necessary amount, which leads to a pileup of near contact neighbors.
Can I ask a question from here? Sure. This is trying to answer the question of what's the protocol. And I'm trying to find it. There appears to be, in the old days, there was a protocol known as Baker's protocol. How bakers make cakes and stuff. I'm trying to find it on the net. There appears to be thousands of references to Baker's packing
Baker's
protocol.
map.
Okay, so no, this is a baker meaning a bakery.
Yeah, but the Baker's map is exactly that.
Yeah,
but
yeah.
It's a,
So there is a protocol apparently.
I don't
and have
think-
been known for centuries of how to get bakers. This is what it's showing. But anyway, so that's one question. The second question was, in the old days, the liquid, if you just looked at a regular liquid and did a structure factor thing, in your Pac-Man, the Pac-Man appears to be very sharp, pointy things. Is that important, or it could be?
it seems to be characteristic.
And it's a cusp with definable things.
I haven't looked at it carefully enough to make a statement like that, but on a
But
cursory viewing, it looks to be, yeah.
We used to usually define that appearance of the split double peak.
Yeah.
Second peak as the appearance of a glass. And this was very, very old times. And I don't know what that reason was.
Say about it is we long ago looked at the second peak in hard sphere fluids below the freezing density, where the peak begins to split. And this was surprising precisely because of what you said, which there was the folklore that, there is some connection to the emergence of glassy behavior, because what it reflects is the onset of well-packed structures locally, right? But that happens in hard sphere fluids below the freezing density, which is clear proof that it really has nothing to do with glassy behavior, right? But you should also expect it in glasses because they are energetically stabilized compared to the fluid.
Okay, I just had a question about the hyperuniformity. Do other ways of constructing random close packings give the same hyperuniformity exponent?
Empirically, yes.
Okay, so
Yeah.
it does appear to be in the Manna class, even independent of constructing it via a Manna kind of process.
I mean, but there you have maybe two data points, right? Because you have two dimensions and of bidispersed, let's say, disks, and then you have monodispersed spheres. So you can conclude what you'd like to conclude, but it's certainly suggestive.